Hey guys, welcome back. And in this video, we're going to talk about chemical equilibrium and free energy, right? And so the equilibrium constant K. What does the equilibrium constant K do? It tells us how far a reaction will proceed. Right, K tells us how far a reaction proceeds. So of course, K is equal to the concentration of products all over the concentration of the reactants. So that's what K does. It's the equilibrium constant. Now, K can be a few values. All right? And we'll talk about that. But we got to go back to delta G here. What does delta G do? Right? Delta G tells us if a reaction is spontaneous, right? Because delta G standard for a reaction is proportional to negative T delta S standard of the universe, right? And, at least in Chem 2 it is, and is the theoretical maximum amount of work. Right? Well, let's not write it that way. How about it's the theoretical maximum amount of energy available to do work. All right, that's better. I like that. Now, this is at standard conditions. What are our standard conditions? Oh, my writing. All right. So thermodynamically, it's 1 atmosphere of pressure. It is 298 Kelvin, 1 molar for solutions, right? Now, delta G equals delta H standard and this is all for the reaction. Or system, however you want to put it in. All right. So we have what K equals, how far a reaction goes, and if it's spontaneous or not. All right. So if the reaction is spontaneous, that means K has a value and delta G has a value. All right. And so for K, for a reaction to be spontaneous, K means it must be greater than 1. And delta G needs to be negative. If it's non-spontaneous, K would be less than 1. And delta G would be positive. And then we can be neither product or reactant favored. All right? Where K would equal 1 and delta G would equal 0. So that's kind of what we have with this. This is the big picture. What does K tell us? The equilibrium constant. Oh, we got more products than reactants. Or we have less products than reactants. And delta G, oh, yes, this is a spontaneous reaction. Or no, it's not a spontaneous reaction. That's what we get. Now, how are they related? All right? How are they related? Okay, well, delta G standard for a reaction is equal to your gas constant, the temperature, times the natural log of K. That's how they're related. So your equilibrium constant, if it's a big number, if K is a big number, it means it's definitely product favored. If it's a small number, it's reactant favored. And then, because if K is big, this is actually a positive number, but delta G needs to be negative. So the actual formula is negative RT ln K. All right. So that's for standard conditions. All right. And at equilibrium, K equals Q, right? And Q is the reaction quotient. All right. So these are at standard conditions and when K is K. What about non-standard condition? That's the next question. What happens at non-standard? Well, what do I mean by that, right? Well, what's an example? H2O liquid going to H2O gas, and delta G, standard for the reaction, is equal to 8.59, positive. Well, we just talked about this. If delta G is positive, we are non-spontaneous. However, everybody knows that water, even at, let's just call it 25 degrees Celsius or 298 K, same thing, right? So water evaporates. If I spill some water on my desk, it will evaporate. But yet delta G is positive by 8.5 kilojoules per mole. You're spilling a mole of water, very realistic, right? 18.2 milliliters of water, you spill that. As long as it doesn't do water damage to whatever, like the wood or something like that, or the floor or whatnot. Let's just say it's on a table that can handle 18 milliliters of water. It will evaporate and nothing will happen. So what's going on there? All right. So writing down, it takes energy to vaporize water. Yet, water evaporates at room temperature. Why? Well, it has to be the conditions. So let's just put it this way. Delta G standard for this reaction does not change. This is standard conditions. All right, so standard conditions, it's not going to change. However, there are non-standard conditions. And so you get delta G. All right. And then we'd have RT. Instead of the natural log of K, we have the natural log of Q, the reaction quotient, which are the conditions. Right? So obviously T is a condition. That's a condition that changes. Q is going to change. Right? So delta G in blue here, this delta G can change based on the conditions. The red one is fixed. That's what it is at 25 degrees Celsius, 1 atmosphere, to the best of our knowledge, right? As new techniques come along, we might adjust, people might adjust that. There's always a new edition of it's called it's a CRC, the Handbook of Chemistry and Physics, right? And I'm looking at it right now in my office, the 100th edition, which is from 2019 to 2020, and they make a new one every year. And sometimes things are updated because new techniques, new discoveries, new compounds, all that stuff. Right, but for the most part, delta G standard is not going to change, especially in Chem 1 and Chem 2. Not changing. All right, R is not changing in Chem 1 and Chem 2. The temperature can change, and that will change. If the temperature changes, this term changes. Right, if Q changes, right, and Q for this reaction up here would equal to the pressure of H2O over 1. Right, because we don't put liquids down there. And so since the pressure of water in the atmosphere is not 1, right, and we're not at, let's say, 100% relative humidity, right, because that matters too. We're not going to get into that. But because the atmospheric pressure is not 1, we're not standard conditions, so water can evaporate. Now, if it gets really humid, like where I'm at in the summertime, water doesn't evaporate so well. But if you live, where it's dry, water evaporates really quickly. Right? And so that's the conditions. All right? And so that's how the free energy can change. Even though you have a non-spontaneous reaction, it can become spontaneous because the conditions will allow it. Right? So the conditions determine what's going to happen. That is what we're going to do with free energy and equilibrium. All right? So that's it. If you have any questions, do not hesitate to reach out. Otherwise, we'll see you next time, guys. Take care.